Previously in Chapter 16, we've looked at electric charge. Now we're moving on to Section 16.2, which covers electric force. When objects with electric charge move near one another, they can experience either attraction or repulsion, depending on the sign of the charge. As objects become closer, this electrical charge between them becomes greater. So we see that the electrical charge between objects is proportional to the product of the two charges. So I've written below charge is proportional to Q1, which is this first charge. I've drawn it as positive in this scenario, and Q2, the second charge, which is negative. And I've also drawn R, the distance between them, to represent that that also affects the strength of electrical charge. In order to determine the electrical force acting on an object, we use Coulomb's law. The law states that the electrical force on an object equals the Coulomb constant, which is written as K sub C, and it equals 8.99 times 10 to the 9th, and then these complicated units, newtons, meters squared, divided by Coulomb squared. So all of that times the first charge times the second charge, we write that as Q1, Q2, divided by R squared, which is the distance between the objects. And in situations where the objects are larger than just points, we measure the distance between the centers of the objects as R. When there are multiple electric charges present in a certain situation, we use the resultant force to calculate charge, which is the vector sum of the individual forces on an object. So if we have these multiple force vectors, we could add them up to find this resultant electrical charge. In this way, electricity is sort of related to mechanics, as we've studied previously. This property is known as the principle of superposition. There are also some cases with these forces in which the vectors add up to zero, meaning that there is zero resultant force. When this occurs, the object is said to be at equilibrium. Because electric force can act on objects without physical contact, it's somewhat similar to gravitational force. However, there are a few important differences between the two. The first is the relative strength. Electrical force, even though it occurs on a very small scale, is relatively much stronger than gravity. The second difference is that gravitational force always attracts, whereas electrical force can either attract or repel, which again depends on the sign of the two forces. Now it's time for some practice problems. Number 1. Two identical conducting spheres are placed with their centers 0.3 meters apart. One is given a charge of positive 12 times 10 to the negative 9th coulombs, and the other is given a charge of negative 18 times 10 to the 9th coulombs. Find the electric force exerted on one sphere by the other. So we know that we have these two spheres. They're placed at 0.3 meters apart. The first has a charge of positive 12 times 10 to the negative 9th coulombs, and the second is negative 18 times 10 to the negative 9th coulombs. Now, they're really just asking for the magnitude of this electric force, so we can sort of ignore the signs for now. This problem is going to require that we use Coulomb's law, which we've learned is F equals Coulomb's constant times the first force times the second force divided by the radius between them squared. So we'll call this force Q1, and we'll call this other force Q2. And now we're ready to solve. So I'll plug in. We know that Coulomb's constant is 8.99 times 10 to the 9th. The first force will be 12 times 10 to the negative 9th coulombs. The second is, we'll just call it positive 18 times 10 to the negative 9th coulombs, and then we're dividing by 0.3, which is squared on the bottom. If I simplify this, I get that the force of these two objects on one another is equal to 2.2 times 10 to the negative 5th newtons. Number 2. 3-point charges lie along the x-axis at x equals 0 centimeters, x equals 3 centimeters, and x equals 5 centimeters. Calculate the magnitude of the electric force on Q2, which is the second charge, when Q1 is 6 times 10 to the negative 6 coulombs, Q2 is 1.5 times 10 to the negative 6 coulombs, and Q3 is negative 2 times 10 to the negative 6 coulombs. So first I'll draw these charges along the x-axis. We have an axis here. That's 1, 2, and 3. And then we'll call this 0 meters. This distance is going to be 0.03 meters, because that's 3 centimeters. And then this distance just between 2 and 3 will be 0.02 meters, because 0.03 plus 0.02 is 0.05, which is the total distance. So we're going to start by solving for the force of 1 on 2. We'll call that F and then 1, 2. That's going to equal Coulomb's constant, which is 8.99 times 10 to the 9th, times, and then the magnitudes of the two forces, which are 6 times 10 to the negative 6th and 1.5 times 10 to the negative 6th, and then I'll divide that by 0.03 squared, which is the radius between them. When I simplify all of this, I get that the force of 1 on 2 is equal to about 89.9 newtons. Now to solve for the force of 3 on 2, which we'll add on to find the total force that's being exerted on charge 2. So F3, 2 will equal Coulomb's constant, 8.99 times 10 to the 9th, times the first charge, which is 1.5 times 10 to the negative 6th. The second will be 2 times 10 to the negative 6th. And then we'll divide by 0.02 squared, because that's the new radius. If I simplify this, I get that the force of 3 on 2 is equal to about 67.4 newtons. Now to find the total force, or F total, that's exerted on 2, I'll add. I get 89.9 plus 67.4, which is equal to about 157 newtons. Number 3. A charge of 2 times 10 to the negative 9th coulombs is placed at the origin, and another charge of 4 times 10 to the negative 9th coulombs is placed at x equals 1.5 meters. Find the point charge between these two charges, where a charge of 3 times 10 to the negative 9th coulombs should be placed so that the net force on it is 0. In other words, so that this third charge is at equilibrium. So essentially what this situation would require is a net force of 0, meaning that the force of this first charge on the central charge would equal the force of the second charge on the central charge. So, and then we can visualize this. We have this first charge, which is the 2 times 10 to the negative 9th coulombs. We have the second, which is 4 times 10 to the negative 9th coulombs. They're 1.5 meters apart, and then we're finding some location for this third charge so that it will be at equilibrium. So let's set the forces of the two other charges equal to one another. We'll start by the force of this first charge over on the left. So that will be equal to Coulomb's constant, 8.99 times 10 to the 9th, times the first charge, which is 2 times 10 to the negative 9th, times the central charge, which is 3 times 10 to the negative 9th, and then that will all be divided by this radius between them, which we'll call x squared. Now on the other side, I might run out of room here, but we have Coulomb's constant again, 8.99 times 10 to the 9th. We have the central charge, which is 3 times 10 to the negative 9th. We have the rightmost charge, which is this, 4 times 10 to the negative 9th. And then divided by, and this time we'll call the radius 1.5 minus x, because it's this total distance minus the little part over on the side. And then that'll all be squared. So right away you can see that we could cancel out these 8.99 times 10 to the negative 9th from both sides, and also that we can get rid of the 3 times 10 to the negative 9th, because those are values that are on both sides of the equal sign. Now we're left with 2 times 10 to the negative 9th divided by x squared equals 4 times 10 to the negative 9th divided by 1.5 minus x squared. And we're solving for x. So if I cross multiply, I get 2 times 10 to the negative 9th times 1.5 minus x squared equals 4 times 10 to the negative 9th x squared. And I can divide both sides by 2 times 10 to the negative 9th to get that 1.5 minus x squared equals 2x squared. Now I will FOIL this expression down here. I'm running out of room again. I'll be doing this over on the side. So I have 2.25 minus 3x plus x squared equals 2x squared. I'll subtract the 2x squared from both sides. and I get that 2.25 minus 3x minus x squared equals 0. So at this point, I could plug this all into the quadratic formula, but instead I'm going to graph it on my calculator and find the 0. So that's what would be happening off screen, or what you could do with your own calculator. But when I simplify all of this to solve, I get that x equals 0.62 meters. So that's how far away from this origin over here that the charge would have to be placed so that it's at equilibrium.